everyone, this is Professor Robert Solis. Welcome to this video lesson. What we're going to do is we're going to take a look at the blackout problem that we worked on last time, but this time we're going to make the program way more efficient by using arrays. So I've created a presentation to help guide you in terms of how we are going to approach this problem. So as you can see over here, this is the blackout with arrays problem. And actually, before I give you the presentation, let's take a look really fast at the execution of the program. So if I were to run this program, you'll recall last time, the way that we played the blackout game is anytime you click a button or a cell, that button swaps its color from white to red, red to white, and any adjacent button also swaps from white to red, red to white. So for example, if I were to click a corner button, this will turn red, this will turn red, this one will turn white. So let me go ahead and click it. Voila. All right, you'll notice that this button was not clicked, and that's because it's a diagonal button. So only adjacent buttons are swapped. So the goal is to make it so that we change all of the colors of the buttons to all white or all red. So for example, if I were presented with a puzzle like this, let me go ahead and solve it in a couple of moves. So if I click over here, here, and here, you'll notice now that I've won the game. In fact, if I click on any of these buttons, can you hear this? Can you hear me clicking on the mouse? It's not going to work. Why? Because I've solved the puzzle, and so we can't go forth. The only way to continue is to click the reset button and then go from there. You'll see that it gives me a moves counter. It took me 14 moves to solve this. I can click reset, and then it's randomly, every time I click reset, it's going to give me a random puzzle scenario. All right, so that's how we play the game. To give you a recollection, last time the way that we solved this was to take a program for every single one of these buttons. So I have a total of 9 buttons, 9 separate chunks of program to say, how do we solve the problem if the user clicks this button? How do we solve the problem if the user clicks this button, and so forth and so on. Now, that was a very easy way to approach this program, and it was very understandable. The problem is that it's not efficient. So if we're crawling, that previous approach was the best approach. But if we want to get to walking or running, the approach that I'm going to show you now using arrays is a much more efficient and elegant way to solve this problem. All right, so before we continue, let me give you an introduction to show you the analysis part, because as you'll recall, Microsoft and Apple, they recommend 75 to 80% analysis and only about 15 to 20% coding. So we are going to focus on the analysis, and then we can go ahead and jump into the code. All right, so I've got a quick presentation to give to you. So this is going to be blackout with arrays, and you'll recall that this was the initial setup for our blackout game. Everything is going to be divided into rows and columns. A row, as you'll recall, goes from left to right. A column goes up and down, right? So this would be row 1, 2, and 3. This would be column 1, 2, and 3. Columns stand up and down. Now, what we want to do is we want to make it so that all we have to do is click on a button as if I were clicking on the center button. And if I click on the center button, you know that the button above, below, to the left, to the right, and the button that we actually clicked, those are the buttons that get swapped. So for example, if I click this center button, this guy would turn to white, 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 and the center one would turn from red to white. All right, that is so elegant to be able to click a button and then above, below, left, right, and the one that I clicked, those are the buttons that need to be swapped. That would be a wonderful approach if I could treat the entire program that way. The question is, can I? So let's take a look at this next slide. Here's the problem. If the user clicks a button on the upper left-hand corner, well, certainly we can swap a button below, certainly we can swap a button to the right, and we can swap the one that was selected. Here's the problem. We don't have a button above, we don't have a button to the left. So this approach of swap the one above, below, to the left, to the right, and the one that was actually clicked does not work in this scenario because 2 of the buttons are missing. Professor Solis, we don't have a button above, we don't have a button to the left, so this falls apart, this approach falls apart. Well, maybe not so fast. Maybe it doesn't fall apart so fast if we do something elegant. Are you ready? Here's the elegance. By creating phantom buttons around our game setup, we solve this problem of no matter what button you click, the button above, below, to the left, and to the right, those are the ones that are swapped. Check this out. So if I were to click this button below would be swapped to a different color, namely white. This one would be swapped. This button itself would be swapped. And look at this. I have a button above and I have a button to the left. So I need to create phantom buttons. Professor Solis, what's a phantom button? It is a button that does not exist in terms of its visual appearance, but it exists in memory. Put another way, if I were to take a look back at our Visual Studio Code, you'll see that in Design View I have my 9 game buttons. But what I'm actually going to do is, in memory, I'm going to create these outer perimeter buttons. You don't see them in Design View as we're looking at Visual Studio, but they will exist at execution by forcibly placing buttons around the perimeter, and now I can use those. Even if the user clicks this button and in memory something swaps, well, it swaps only in memory. It doesn't actually swap in terms of the visual presentation of this program. But the reason why I do that is because it helps me solve the problem of, can I just make it so that no matter what button I click, the one above, below, to the left, to the right, and the one that I clicked gets swapped. And this solves that problem. All right, so in order to do that, we've got to come up with a naming convention for these various buttons, and that's what we've done here. So what we'll do is we'll just simply use the coordinates that we've established for all of our rows and all of our columns. And the first number itself is going to represent the row, and the next number is going to represent the column. All right, so for example, if I were to take a look over here at btn3 underscore 1, the first number represents the row, the second number represents the column. This is a very elegant approach for a name because the name itself also indicates the location of that button. Namely, you're going to tell me what row and what column you represent. All right, let me go back a couple of slides. So that's the naming convention that we're going to use for all of these buttons. For example, over here, this button is located at row 2 and column 3. Let's verify. 0, 1, 2. Yep, that's the 2 right there. 0, 1, 2, column 3, and that's the 3 over there. So we were able to get that done. All right, now that I have this approach, I can swap above, below, to the left, and to the right, and the button that was clicked, because I have a button above, I have a button to the left, to the right, below, so forth and so on. In fact, what we're going to use is what's called subscript mathematics, and I'll go into this in the future video lesson. But just to give you a quick preview, if I were to take this button, say for example, you know that this button and the one below need to be swapped because all adjacent buttons are going to be swapped. All right, well, row 2 minus 1 is row 1. So if I take that number and subtract 1, it tells me what row button to select, to swap. Woohoo! All right, if I take this button, the column button, and subtract 1 from it, it tells me what column button. Oh, so 2 minus 1 is 1. Ah, that's this guy. All right, 2 plus 1 is 3. That's going to be this guy over here. The row. So sorry, this guy over here. And then 2 plus 1 for the column is 3. That's going to be this guy over here. And so if that didn't make sense, that's okay. That's a little bit of a preview of what we're going to be doing in terms of subscript arithmetic or subscript mathematics to be able to define what does it mean above, what does it mean below, or to the left or to the right. We're going to use this naming convention to help us out. All right, so that's it in terms of the presentation. Now what we need to do in the next video lesson is we need to take all of that idea, that concept, that analysis, and churn it into the C# code to make that happen by creating various methods. So we're going to create a game setup method. We're going to reset whenever the user clicks the button. When you load the form, what do we have to do? What setup do we have to perform? When you click a particular button, what are we going to do? What does it mean to swap a color from red to white, white to red? What does it mean in terms of setting up our game? All of this stuff we've got to go over. Now, you'll see that we have approximately 173 lines of code, and that was much less than our previous attempt using the different algorithm, which was required something like 500 or 600 lines of code. This is going to be a much more efficient approach, a little bit more difficult in terms of the concept, but way better in terms of the efficiency and the beauty and the elegance. And that's ultimately what we're trying to head towards as computer science students. All right, so this is Professor Robert Solis. I hope this video lesson was helpful. Have a good day. See you next time.